All right, we're going to talk about frequency response and transfer functions today. Frequency response, you probably have a feel for what that is already. It's going to end up being something like a graph of frequency versus, voltage or current gain. And if we were talking about like the resonant frequency of something like a simple RLC circuit, you might have a low gain, but then at a certain frequency, like the resonant frequency, the gain would go up really high at that point and then come back down. So that's an example of a frequency response. Now, circuits, the RLC circuits, are going to have a frequency response because the impedance of the elements depend upon frequency. For example, J omega L, the inductive reactance, depends on frequency, or minus J over omega C. The capacitive reactance depends upon frequency. So there's going to be some sort of frequency response that's not going to be the same at every frequency. We need an easy tool then to deal with that, and there's a fairly easy tool, and it's this type of frequency response plot like that. Oftentimes this is presented as a logarithmic plot, and whenever it is presented as a logarithmic plot, these are called Bode plots. Now, Bode plots are something we're probably not going to spend a lot of time on in this specific class, but as you go forward in electrical engineering, or if you take the second semester of a linear circuits class, you're probably going to spend a lot more time on those than we will in here at all. Okay, transfer functions. Transfer functions are a way to look at how energy is transferred. They're network functions. They show up not just in electrical engineering, they also show up in mechanical engineering. So it's a generic term, and it's going to be symbolized in this class this way: H, which is going to be a function of the frequency. Now, H is a phasor, and you can see that that phasor is frequency dependent. Now, the definition of a transfer function is this: it is some output relative to some input. And usually this output and that input are both going to be phasors themselves. So something like voltage gain. Voltage gain could be thought of as a transfer function. So you're going to have some V output versus some V input. And again, those would be phasors. And they would be dependent upon frequency. Like that. So this voltage gain would be an example of transfer function. You could do the same thing with current. You could do the same thing with, let's say, transfer impedance. You could do anything where you're taking the relative ratio of output to input would be something that's a transfer function. Now, transfer functions then in general are phasors, and you have some kind of numerator and some kind of denominator, and those are phasors as well. Now, that's output over input ratios. Now, like I said, probably a little later on in your electronics career, you're going to be dealing with Bode plots. You'll also be dealing a lot more with transfer functions. Our goal in this section is to introduce these things, maybe use them a little bit, but you're definitely going to use them more later. Something regarding transfer functions are things called zeros. Zeros are where you have the transfer function equal to 0. Now, where does that happen? That happens where you've got this numerator equal to 0. So where is that equal to 0? Well, you just set it equal to 0, and that tells you where the transfer function is 0. So those are called zeros. That makes sense. The other thing are called poles. Poles are really where the bottom is 0. And if you think about that, when the denominator is 0, the transfer function is going to be infinite at that point. So you'll spend some time finding poles and zeros as you get further and further into transfer functions. Okay. One other thing regarding transfer functions: if you have the magnitude of a transfer function, we're going to call this the gain. So the gain is the magnitude of that phasor there, and that will be something we use a time or two in this section. Okay, but the reason we want to introduce frequency response and transfer functions is because we want to talk specifically about filters. And what filters are, it's a way to filter out certain frequencies from a response. And filters come in a variety of configurations. If we have a plot of frequency versus gain, then down here would be 0 frequency, and then frequency would increase up to potentially infinity here. And if we wanted to just see or just be able to measure the low frequencies, that would be the ones closer to 0 down here, then we might have a gain that is high for those frequencies, but at some point we'll cut that off, and then the gain would be effectively 0 down here. So that frequency, let's call that omega sub c, that's omega cutoff, would allow the low frequencies to pass through, the high frequencies would be cut off. So we would call this a low pass filter. Okay, because it's allowing the low frequencies to pass through. I remember what that gain is. That gain is going to be a transfer function, the magnitude of that transfer function, which we have said is going to be voltage output versus voltage input. Everything's a phasor here. Okay, so this would be a low pass filter because it's allowing the things that have low frequencies to pass through. This region over here, this is the band pass, and this region over here, this would be the band stop. So between the band pass and the band stop is the cutoff frequency, and you can see how that might work. Now, this is an idealized case. Never is it going to be the case that the cutoff frequency is so sharp like that. We're dealing with realistic, real-life components, so it's probably going to look something more like this, that it's going to be a smooth curve that maybe does something like that. Hopefully you can see that. But there's a relatively smooth curve right there, not this discontinuous type of function. Then the question becomes, all right, well, it's kind of obvious in the dark lines there where the cutoff frequency is, but it's not so obvious on this smooth curve here exactly where the cutoff is. So we'll define the cutoff a little more clearly later on, but it's going to be about 70.7% of the total, whereas this has a maximum gain of, say, 1, and down here is gain of 0. It's going to be 0.707 of the total. So 70.7% of the maximum values will be somewhere right around there, and that cutoff frequency corresponds to that value of gain. Okay, but we're just describing what a low-pass filter is at this point. Filters come in other configurations. For example, you could have frequency stop, band stop at the low frequencies, and then band pass at the high frequencies. So it might look something like this, where this is be the cutoff. Again, this is gain, and this is the stop region, the band stop region, and this is the band pass region here. Once again, It's not going to be in reality such a discontinuous function. It's probably going to look something more like that. So the cutoff frequency won't be so clearly defined. But the point here, while we're just introducing these, is that the high frequencies are the ones that are being allowed to pass through. So this would be a high pass filter. Okay, so we've got low pass and high pass filters. You can imagine that you could work in some configurations that have effective combinations of these two, and you could have something that allows only a specific region of frequencies to pass through. And so this would be the stop region, this would be another stop region, and this would be a pass region. And you would have two cutoffs. You would have a WC1, omega C1 and omega C2 here, frequency versus gain. And now what you've got is just a certain bandwidth that is allowed to pass through. So this one could be a band pass filter. Okay, the inverse of that could also exist. So we have pass regions on either side of a stop region. So this would be the band pass, this would be the band pass, and this would be the band stop. And you still have two cutoff omega C1, omega C2, gain versus frequency, like that. Okay, now in this case, we're stopping or rejecting, or you can see there's a gap in the frequency response there. So this goes by a series of different names, as some of these also have slightly different names. So this is going to be the band reject filter, because we are rejecting or stopping these. This could also be called a band gap filter, a band stop filter as well. All right. Now, all the filters that we're going to talk about are considered passive filters. And the reason they're considered passive filters is because they involve the passive elements that we've used throughout the whole semester. So that's the Rlc components. Those are the passive components. Now, that's opposed to active elements. Active elements would be things like op amps or transistors, or some other type of element that can generate its own energy, whereas an RLC component can't do that. All right, well, let's get right to it and talk about low-pass filters. There's a number of ways that you could do a low-pass filter. We're going to use RL circuit components with a sinusoidal source to create a low-pass filter. This is a pretty simple type of filter to make. So we've got some sort of sinusoidal source there, inductor, and a resistor. So this is our R value, this is our L value, and this is our V sub I, that's the input. And what we're going to be interested in is what is the output across that resistor, what is the voltage output across the resistor. Now the input voltage, V sub I, is going to be our typical sinusoidal source, so a cosine omega t plus some phase angle phi. Now, if we were doing this, building this with a bench instruments, or perhaps you're simulating it in software, then you would choose a source that has a modifiable or changeable angular frequency. So the omega could sweep some range. And that range is going to allow you then to compute what the output is relative to the input, and then you'll be able to create some sort of frequency plot, like a Bode plot or something. For us, we're going to think this through, and I'm going to give you some help along the way, but this omega here is what we're going to change as we go through this analysis here. So the omega is going to sweep from 0 to well, essentially infinity here. Now, let's consider what happens for the extreme cases here. If I take this circuit, which is currently in the time domain, and I transform it into the frequency domain, then let's see what I end up with. It's going to be, this is phasor V input, this is going to be J omega L, and this is still going to be R, and this is going to be phasor V output. Okay, just like that. Now, think about what the output here is going to look like. This is not a difficult problem to solve. Phasor V output is going to be the ratio of R over R plus J omega L times V input, like that. So the ratio of output to input is going to be V output over V input, phasors. It's just R over R plus J omega L. Okay, that right there is a transfer function. So let's think now about what's going to happen here if we are at the extremes of what the frequency can be. So what if omega equals 0? What's going to happen here? Well, in that case, the J omega L is going to be 0. So the impedance of the inductor is going to be 0. And when that happens, this circuit is just, this circuit is just a resistor and the source at that point. So the circuit becomes that. The inductor might as well not even be there. So that reduces it down. It becomes a pretty simple answer at that point to figure out what V output is, because it's just going to be the input. Okay, well, that's a pretty straightforward case. That's what you get if you have omega equals 0. Now, what about at the other end? What if you have omega equals a very, very high number? So let's just say omega equals infinity. Well, at omega equals infinity, the impedance for the inductor is infinite. So in that case, well, it's as if the inductor is not there, but it leaves behind a gap. Rather than it being treated like a piece of wire, now there's a gap right there, and we've got the output across the resistor is going to be nothing. So this is what you get if you have an infinite omega. But between these two extreme values, we're going to have some sort of response that is going to look like this function here. And you can see that it does depend upon omega. It's inversely proportional to omega here. So if we were to take this and we were to create a plot, let's say we plug this into, MATLAB or some sort of, even Excel, and generated a bunch of numbers that we could plot, then here's what we would get out. We would get out a plot that looks something like this, where this is our frequency versus our gain, which is the magnitude of our transfer function, which you recall is just V output versus V input, magnitude of that right there. And this is the voltages that we're measuring across the resistor. And let's say the maximum value that it's going to be is going to be 1. Okay? And then over time, as we plug in different frequencies, so this is 0 here, 0 frequency, but as we plug in different frequencies, we're going to get something that looks roughly something like that. And it's going to reach 0 here in the limit. Okay, so it reaches 0 in the limit. Now there comes a point here somewhere where we'll say that that represents the cutoff frequency. In other words, the output response has become small enough that we'll say anything that's below that level right there, anything that's below that means that the response is effectively not there. So we'll say that that's our cutoff frequency. Now that turns out to be at 0.707. Now that 0.707 may look familiar to you because that's really 1 over the square root of 2, which is the same thing as square root of 2 over 2, which is the same thing as 70.7% of the max. So once the gain reaches below 70.7% of whatever the maximum value is, then we'll say it's effectively reached 0, and that frequency at which it does that, that is the cutoff frequency. Now, it turns out as you go into this and you learn about Bode plots and so forth, that turns out to be about 3 dB below the max. It turns out that 3 dB is about 0.707 units of whatever you're measuring here. So you hear engineers talk about the 3 dB roll-off point there. Okay, so the cutoff frequency is right there at that. Now, I'm just giving you that. I'm not really proving that to you or anything. All right, well, cutoff frequency is omega sub c. So omega sub c is where h j omega is equal to 70.7% of whatever h max is. Okay, transfer function max. It also turns out that that is the point where power is 50% of whatever the maximum power is. Okay, so sometimes that point is called the half power frequency. So the cutoff, omega sub c, is the half power frequency where the cutoff occurs. All right, well, for our problem that we've got here, when we transform into the frequency domain and we determine what our transfer function is going to be, I've already said that we've got V output over V input. That's going to be R over R plus J omega L, like that. Well, that's one way to write it. That's typically that's not the normal way to write it. You usually want to write it in terms of, well, actually in terms of the tau, which is the time constant. And let's do a little bit of rearranging here and see if we can't come up with that. First of all, I'm going to divide the top and bottom by L. And when I do that, I've got R over L divided by R over L plus J omega, like that. Okay, now we've reached a point where this is actually 1 over tau. Okay, and you'll notice that since we're talking about specifically an RL circuit, this is the inverse of the time constant. Okay, now it's not real obvious. The J omega is on bottom of this fraction here, but this could be rewritten in this sort of form. You could have a real part plus a J imaginary part. You know, with a little bit of algebra manipulation, you could change this around where you've got the real part up front, you've got a J omega part in the back, and it would be in rectangular form at that point. You could do that, okay? You could also write it in terms of a polar form. And whenever it's in polar form, you end up with a magnitude times an angle, which is also a function of the frequency. And that is your transfer function. This whole thing right here is also your transfer function. And remember, I haven't really been careful about this, but everything here is a phasor. Okay, so the phasor can be expressed in a rectangular form or a polar form like that. Now, rather than go through the process of the algebra to get to that point, I'm just going to jump to the solution and show you what it looks like. The magnitude of this specific transfer function is going to be R over L divided by the square root of omega squared plus R over L squared. Okay. Now, this is sort of a hand-waving argument, but it really isn't that bad to be able to go through this. What you would do is you take this part right here, you perform some algebra tricks to get the J in one term so that you have a real number in the first term and an imaginary number in the second term. After you've got it to that point, you would multiply by the complex conjugate to figure out what the magnitudes are, and the angles are as well. That's just a conversion between rectangular and polar form in order to do that. It's honestly not that difficult, but I don't want to take up any more of your time. Okay, so this is the magnitude of the transfer function, but you also have the phase angle, which is minus the inverse tangent of omega L over R. So if you went through the process again, you could show that those are true. Okay, so that's kind of important to you if you're trying to figure out what the magnitude of the transfer functions are, or that phase angle. But what we want to know is how do you find that cutoff frequency, because that's probably something that's going to be important to us, especially if we had to build a low-pass filter, and we want to know at what how do we find that cutoff frequency. First, notice a couple of things here. We've said that at omega equals infinity, okay, what is the transfer function? Well, the magnitude of the transfer function at infinity is going to be this, with infinity, a very large number, infinite number plugged in for omega here. So it's going to end up being R over L over a very large number. And what is that going to be? That's going to be 0. So it makes sense that it goes to 0 as omega goes to infinity here. Okay. Also, well, what happens to this at infinity? Well, theta at J infinity is going to equal, let's see, minus inverse tangent of, well, a very big number. And where does that happen? At minus 90 degrees. So even though the magnitude of the transfer function goes to 0, this turns out to be a real angle at negative 90 degrees here. All right, well, where then is the magnitude of the transfer function equal to its maximum value? Okay, well, look back here. Its maximum value is going to occur when the omega down here is 0, because then this denominator is as small as it can possibly get, which makes the magnitude of the transfer function big. Okay, the R over L is going to remain the same. Those are fixed values. The thing that we're changing here is the frequency. So when the frequency is as small as it can possibly get, which would be 0, then that's where the max occurs. So that occurs at omega equal to 0 there. And that cutoff frequency occurs, so W sub C occurs when the magnitude of the transfer function is equal to H max divided by square root of 2. Okay, and that is the point where it occurs. So H max occurs at omega equals 0, but the cutoff frequency occurs where the transfer function is H max over square root of 2. Okay, and that's what I gave you back here at square root of 2. That's the 0.707. That's where that occurs. All right. So let's see here. The H max occurs at 0, so we could say H max is the same as H J0 magnitude divided by square root of 2. We could do that. All right, so what we want to find then, because we want to find that right there, and then we can divide by square root of 2. That would be one way to go about it. We know that that's 1 already. So really we're after a way to get to this cutoff frequency here. And it's really straightforward. So let's do that. I want magnitude h at j omega c, and we know that that's equal to 1 over the square root of 2, and that occurs r over L divided by square root of omega sub c squared plus r over L squared. Okay, so there's the equation that we need, and we need to solve this for omega sub c. And that's just algebra in order for you to go through that, but here's what you'll get when you go through this. Go ahead and do this. Prove to yourself that this is the case. You really only need to worry about the final result here, though. Omega sub c is equal to r over L. That's the point at which this is a true statement here. And you can go ahead and plug it in and see that it is true, and yeah, it is, okay? Because this is going to be r over L squared. You're going to have 2 of them when you take the square root, so the r over L's are going to cancel, yeah. And so you can probably see that that's the case. So the cutoff frequency can be set then to any frequency as long as this ratio of r over L is maintained. So you figure out what you want the cutoff frequency to be for your filter, specifically your low pass filter here, and then you can make it whatever it needs to be by choosing your R over L components wisely then. Okay? All right. So if that's the case then, let's go through the process of designing our own low pass filter here. And I'll take some space down here. Okay, let's set it up this way. What I want to do is I want to create a low-pass filter that will allow some frequency to pass through and not other frequencies. And a good model for this is the human heartbeat. Normal human heartbeat is about 72 beats per minute. Now, if you round that, that's approximately equal to 1 hertz. Okay, 1 hertz would be 60 beats per minute, but we're getting close to that. All right. What we want to do then is we want to design a filter for an electrocardiograph that needs to detect that frequency right there. So let's design a filter with a cutoff frequency somewhere above this. And we could say we want our cutoff frequency to be above this, and we want to allow for a range of heartbeats, so let's say 10 hertz. We'll make a cutoff at 10 hertz, and 1 hertz is certainly underneath that somewhere. But this 10 hertz cutoff frequency is going to remove noise that is also very ambient in the environment, and that is 60 hertz. 60 hertz is everywhere in the environment. That's the electrical frequency that comes from electrical devices humming, lights humming, and so forth. So 60 hertz is very prevalent in the environment. So a cutoff frequency at 10 would cut out the 60 hertz and other frequencies around there. Once we build our low-pass filter, then let's test it out and let's see what the output is at some frequencies. Let's figure out what it is at 1 hertz. Let's figure out what it is at 10 hertz. And then let's figure out what it is at 60 hertz to see if this one is blocked out This one should easily pass through, and this one is our cutoff, so we know what that needs to be. That needs to be 70.7% of the maximum value there. So what we need to do is we need to select R and L values to get a low-pass filter with a cutoff at 10 hertz. All right, now omega sub c is the radian frequency. So this is in units of radians per second. These frequencies here that we're talking about here are just normal frequencies. So we need to keep in mind that this is a relationship between radians per second and cycles per second. All right, now we want our cutoff frequency to be 2 pi times 10 hertz. So this turns out to be 20 pi radians per second, which is the same thing as 20 hertz. 20 pi hertz. Okay. All right, now that's what our cutoff frequency is going to be, and this is angular frequency now. So omega sub c, we know that that's going to be 1 over tau, and since we're talking about Rl circuit, this is going to be R over L, and that needs to equal 20 pi. Now, there are infinite number of possible combinations of R and L that can meet this, make this a true statement here. Okay, infinite possible values that are solutions to that equation there. But we've got a limited number of quantities, so one of the selection processes might be what's easily available, what's widely available that I can use. Well, let's pick L equals 100 millihenry, and the only reason we're picking that is because that's an inductor that happens to be available, let's say. Then if that's the case, if that's our L value, then our R value is going to be omega sub c times L, so that's going to be 20 pi times 100 milli, that's 0.1. And what is that right there going to be? That turns out to be 6.28 ohms. So what we'll do is we'll choose our L equals 100 millihenry, and we'll choose our R equal 6.28 ohms. And if it turns out we don't have in stock a resistor that is 6.28 ohms, then we'll build one, because we can make resistors higher or lower, equivalent resistors, just by combining things in series and parallel. We'll get as close as we think we can to that, and it should work. So let's see how our selections are going to filter then. Transfer function is going to be h of j omega. That's going to be V output, j omega divided by V input, j omega. Again, everything's phasor here. Well, that makes the output function equal to transfer function times the input. And if I want to know the magnitude of the output, that's just the magnitude of the input multiplied by the magnitude of, or magnitude transfer function times the magnitude of the input. All right, well, we've already figured this out. This is R over L divided by the square root of omega squared plus R over L squared, like that, times this V sub I here. And we know what these values are here. We know that R over L is going to be 20 pi divided by square root of omega squared plus 400 pi squared. Okay, that's 20 pi squared. All right, now that's what our output is. We're really interested in, I don't know why I went through all this trouble, we're really interested in that ratio there. So I'm going to put that back over here, like that. And Well, in order to calculate this value here, I need to plug in for various values of omega. Well, here I can do this like with Excel or MATLAB or something like that, or I can just build a chart here. Let's say I've got my frequency and I want to test it at 1 hertz. Let's test it at 10 hertz, and let's test it again at 60 hertz. Well, that corresponds to omega of, this is going to be 2 pi, this is going to be 20 pi, and this is going to be 120 pi. All right, so if I calculate V output over V input, then this is where you just take these values, plug them in here, and see what numbers you get out for this. And it turns out that V output over V input is 0.995. Okay, so 99.5% of the signal is passing through at 1 hertz. And that's the region of the human heartbeat, so we're getting good response at that point. At 10 hertz, plug in 20 pi here for omega, and you get out 0.707. And that is exactly what you expected. That represents then the cutoff frequency at 70.7% of the max. If you take 60 hertz, which is 120 pi, plug it in here for omega, and do your calculation, you end up with 0.164. All right, that is only 16.4% of the max, which is below our cutoff level of 3 dB from the max. So this, we say, has been successfully attenuated, and remember the 60 hertz is where a lot of the noise is from electrical sources. So we have successfully attenuated any of the noise from our device here. Okay, congratulations, you made your first low-pass filter. Now, we did that using R and L components. You could do the same sort of thing using different components. It's not that you're limited in that way. Let's try it with, let's make an RC low-pass filter. And we'll do that same sort of way. Except instead of taking our output voltage across the resistor, we'll take it across the capacitor here. All right, let's transform this into frequency domain. When we do that, this becomes minus J over omega C. This is still R. This is our phasor V output, and this is our phasor V input. Like that. Transfer function then is going to be H J omega equals that right there. Again, this is very much like a voltage divider. So our transfer function is going to be, let's say, 1 over J omega C. Remember that minus J over omega C, that is equal to 1 over J omega C. I just wrote it this way to alleviate the negative sign. Divided by R plus 1 over J omega C. Okay, and that's the ratio right there. So there's our answer. Now, you can manipulate this, get it into a slightly different form. And here is the form that we'll write our final form in. So it's going to be 1 over RC divided by J omega plus 1 over RC. This is our transfer function now. Okay, so we've got that for our transfer function. Now, to find the magnitude, remember, because it's the magnitude that we're largely interested in. So to find the magnitude, you would put this into its rectangular form, then multiply it by complex conjugate, and you would have magnitude of it. When you do that, you end up with this. And maybe you start to notice some patterns here. Okay, but this is the transfer function magnitude. All right, now to find the cutoff frequency, so omega sub c occurs at the point where magnitude of this is equal to h max divided by square root of 2. All right. So the low pass filter, h max occurs at h at j0, like that. So, and we know that that's equal to 1, so this is going to be 1 over square root of 2, and this is where we get our omega sub c. So we set the transfer function here, magnitude of the transfer function, equal to 1 over square root of 2, and solve it for omega sub c. And when you do that, here's what you get. That. Again, this is 1 over tau for an RC circuit. All right, so let's summarize what we've got so far. So far, we've only talked about low-pass filters. We'll go very quickly through some of the others. But we've got, let's say, 2 different types. We've seen the ones involving R and L components. So there's L, there's R. This is our output and our input. And we've had the other version, which includes R and C components. So there's R, there's R, C, the input, the output. Okay, so we were measuring our outputs across different components in each one of these. Now for this one, omega sub c was R over L, that's where the cutoff occurs. Omega sub c was 1 over RC. But in both of these cases, in general, we could say that omega sub c is 1 over the time constant there. Also, in general, you may not have noticed this, but the transfer function itself is equal to omega sub c divided by j omega plus omega sub c. You probably noticed that pattern. And the magnitude of h j omega is equal to omega sub c divided by the square root of omega squared plus omega sub c squared. So you've seen this now, and you can use this information to build a low-pass filter if you want to. It shouldn't be too hard from this point going forward. All right, build it and then create a graph. You know, we showed a little chart here, but you could do that in Excel and create a whole series of numbers and then plot those numbers if you wanted to, where you're stepping through various frequencies to see what the response is. In other words, you're building your own frequency response curve in that way. Or you could do it in MATLAB or any other type of graphing program like MathCAD. You could probably even figure out a way to do it on Wolfram Alpha if you wanted to. Okay, so that's low-pass filters. Let's do the same sort of thing. We don't have to spend so much time on it now, but let's do a high-pass filter. Okay, so we'll turn our attention to high pass. All right, well, let's start with RC. Here's our input, our capacitor, our resistor, and this time we're going to take the output across the resistor. Okay. Transform that into frequency domain and this is going to be 1 over j omega c, and this is our input phasor. That. Okay, now for this one, tau is RC. So the omega cutoff is going to be 1 over tau, so it's going to be 1 over RC, like that. Okay, now I'm sort of giving that away, but you could probably figure that out if you think back to our example right here. This was our low pass filter, and what we were doing is we were taking the voltage across the capacitor. Well, this is the same problem here, except now rather than taking the voltage across the capacitor, we're taking it across the resistor. Okay, so this taking the output voltage across the capacitor gives you a low pass filter, while taking it across the resistor will give you the high pass. All right. So what does that mean? The curve for this one is going to look like this. It's going to start, that's omega, and this is the magnitude of the transfer function here. Maximum at 1. Starts down here at 0 at 0 frequency, and it does this sort of thing. Rises up and levels off at the maximum. So it levels off at the maximum, and it reaches the maximum in the limit. Then, well, where's the cutoff then? Well, the cutoff is going to be somewhere right around there at 0.707, and this corresponds to the cutoff frequency then. All right, we'll go through the same sort of analysis then very quickly. Transfer function, J omega, is V output over V input. Everything's a phasor here. And when you do that, you're going to end up with J omega over J omega plus 1 over RC, like that. Okay, now that's not a big surprise. This could also be written in the form magnitude, angle, so it can be written in rectangular form. It could also be written in polar form like this. And if you go through the algebra to figure out what the magnitude is, then you're going to end up with omega over the square root of omega squared plus 1 over RC squared, like that. And theta ends up being 90 degrees minus the inverse tangent of omega RC, like that. Okay, now you go through the process once again of setting this up, setting this equal to 1 over square root of 2, solve for omega out of that, and that would be your cutoff omega, because you're setting it equal to 0.707. So you end up, when you do that, with omega sub c equal to 1 over RC, which is exactly what I told you it would be. It ends up being that. Okay. Now, that was for the RC. As you can imagine, since we did an RL first, you can also do that. So let's see. Here was the RL. We were measuring the output across the resistor. Well, now you measure the output across the inductor, and it becomes a high-pass filter. So if you would just, I mean, I'm not even going to show that really, but I will draw it for you and write the answers now. So 0, this is our inductor, here's our resistor, we're taking our output across that. This will be our input. We'll just go ahead and convert this. This is going to be J omega L. Then our transfer function, going through the steps again. We've done this several times now, so it shouldn't be a big deal for you. J omega over J omega plus R over L. And then the magnitude, like that. Okay, and the cutoff frequency, what's it going to be? Which is the same thing as 1 over tau for an RL. Okay, so everything looks very much the same for those filters. So you can see that whether something is a high pass or a low pass depends upon what component you're measuring your output across. All right, well, that leaves high pass and low pass, the simple versions that we'll encounter here. There are more complicated versions. In fact, filters come in all sorts of configurations. But let's move on and talk about band pass. So we're going to talk about band pass filters. And for this one, we're going to need to put all three components, R, L, and C components together. So we'll start off with this configuration. Here's our R, capacitor, inductor, input, source, and what we're going to do is we're going to measure the output across the resistor here. Okay, first thing we're going to do is we're going to transform into a frequency domain. So this is still our resistor R. This is going to be 1 over j omega C, and this is going to be j omega L. Phasor input, phasor output. Okay, our transfer function is just the ratio of the output to the input. So V output over V input, phasors. Okay, and you notice this is another type of voltage divider here. So we could write our output is going to be R over the impedance sum, so R plus j omega L plus 1 over j omega C, like that. All right, now the goal is to simplify this. Part of the logic in simplifying it is you take terms that have j omega in them, and you want to separate them as much as possible, put them aside there. And this one is not very pretty. J omega times R over L divided by j omega squared plus R over L, j omega plus 1 over LC. And that's one way to write the transfer function. Again, not that pretty. Now you can take this, write it in a real and imaginary part, and take multiply by the complex conjugate, and you can figure out that the magnitude is going to be equal to omega R over L divided by the square root of 1 over LC minus omega squared, quantity squared, plus omega R over L, quantity squared, like that. Okay, and then phase angle of the transfer function is 90 degrees minus the inverse tangent of omega R over L divided by 1 over LC minus omega squared. Okay, so those are the values that you care about. From these, you could calculate the output and the input and so forth. However, if you were to graph this, let's say you do the same sort of thing that we did previously. You pick some arbitrary values for R and L and sweep omega across a whole bunch of different frequencies, maybe go from 0 to a very large number. You are then able to create a graph that is effectively the frequency response. And you can graph the magnitude versus frequency. And here's what it would look like. It goes up like this, and then begins to move down like that. And it reaches 0 in the limit. Okay, well, you've got some, you effectively have a maximum value, just like before, of 1. And then the 70.7 or the 0.707 is you're actually going to have 2 intersections here. One there and one there. So you'll have 2 cutoffs. Let's call this one omega sub C1. You'll have another one that's omega sub C2. And then the center of that, which is actually not in the center because this is not symmetrical up here. This curve is not necessarily symmetrical, but you do have an omega naught that represents the center. So the width here, where it's above 70.7%, that width is called the band pass, because that's the bandwidth that is being passed through the filter. Now that is symbolized with beta there. Now you've got a center frequency, that's omega naught. You've got 2 cutoff frequencies, omega sub C1, omega sub C2, and then you've got the bandwidth, which is beta. All right, now all of those quantities can be calculated. Given the magnitudes of this right here, you could go through and you could determine where is this equal to 1 over square root of 2 and so forth, and that would give you the center. And then you could go through and say, okay, well, where is it 70.7% of the max, and then to get your 2 cutoffs, and then the omega naught's the center of that, I should say. Okay, well, so calculate your center frequency, that's omega naught, and that just turns out to be 1 over the square root of LC. That's the resonant frequency. Okay, and you know that. The cutoff frequencies, that's your omega sub C1 and omega sub C2, look a little more difficult because they involve quadratic equations. So it's minus, when you simplify it, it looks like this, minus 1 over 2L plus the square root of R over 2L squared plus 1 over LC. That's omega sub C1, omega sub C sub C2. That is plus R over 2L plus the square root R over 2L squared plus 1 over LC. So you can see the difference here is the sign that's out front here of that first term. Okay, and then there is a relationship between omega naught and omega sub C, and that is this, that omega naught is equal to the square root of omega C1 times omega C2. And you may be wondering, well, why isn't omega sub C just halfway between those two? Well, the reason it's not is because of that asymmetry. It's not exactly in the center. And this is L, it's LC. All right. Now, the bandwidth, though, is just the difference between these 2 cutoff frequencies. So bandwidth beta is just the upper cutoff minus the lower cutoff. And if you do that subtraction, this minus that, well, that's just R over L. And that's the inverse tau for this one. Okay, now when it comes to doing like this sort of trace, let's see, where did it go? This right here, this is a band pass filter, so any band frequency that is above that, so between the cutoff frequencies, is going to be above the 70.7% there. But that depends upon frequency itself. The band width depends upon these frequencies here. So there is something that represents the quality factor, which is the ratio of the center frequency to the bandwidth. So the quality, which we'll just call big Q here, is the ratio of the center frequency to the bandwidth, like that. So if you take your omega naught here, take your beta, this, and take the ratio of those two, this turns out to be square root of L over C R squared. Okay, so you can see what that means here. A narrower bandwidth gives you a higher Q, and a higher frequency for the center frequency here also gives you a higher Q. Okay, so it works out to be this. Now those center frequencies, those cutoff frequencies, they can be written in terms of the R's and L's, but they could also be written in terms of the bandwidth and the center frequencies. So we could write omega C1, this is just an alternative form, that's minus beta over 2 plus the square root of beta over 2 squared plus omega naught squared. And then omega sub C2 is going to be positive beta over 2 plus the same stuff underneath the radical. So beta over 2 squared plus omega naught squared, like that. And there are other ways to write that as well. You could also put those in terms of the Q value. When you do that, that's omega naught times 1 over 2Q. That's minus 1 over 2Q plus the square root of 1 plus 1 over 2Q squared. And then this one, omega naught times positive 1 over 2Q plus the same stuff under the radical. Okay, just throwing this stuff out at you. Wouldn't expect you to have all that memorized or to see how the algebra works out so that these are okay. It's not necessary that you understand that at this point, but we still haven't really talked about the transfer function in some detail. So the transfer function itself is this right here. That can be, and the magnitude is this right here. Well, the magnitude can also be rewritten a little bit. Let's say the magnitude of that transfer function could also be written this way. 1 over the square root of 1 plus omega RC minus 1 over omega L over R. And then that quantity is squared. Like that. Okay. So the magnitude of this transfer function is max when the stuff that is, I'm sorry, let me rewrite it the way that you saw previously. There. So looking at this form of it, the magnitude of this transfer function is maximum when this right here, when that is 0, which occurs, if you'll just set that equal to 0, that occurs when omega is 1 over the square root of LC. So you get the maximum value out of your transfer function magnitude when this is the resonant frequency. So when the frequency of our generator equals the resonant frequency of the circuit itself. Okay. Now at the cutoff frequencies, you could solve for those as well. Okay. Here's some things I want you to notice though. Okay. First of all, let's go back. Let's go back here and look at the quality factor here. I'm going to rewrite that right here. The square root of L like that. For one value of R, I may get something that looks like that. This is what I should be saying. But for a different value of R, I may get something that looks like that. Okay? And for one of these, I may have that as the bandwidth, but for the other one, with the larger R value, I may have something that looks like that. Okay? So the R value helps determine what that bandwidth is right there. So a larger R value, a bigger number here, gives me a smaller Q value. So forget about the scale over here. These are different scales for each one of these. But this is for the larger R, and the upper one is for the smaller R. So the presence of the R changes everything. It changes what the beta value is. It changes the omega naught value. It changes the omega C1 value, the omega C2 value. So just keep that in mind as you think through the process here. Okay, I think I've confused you enough. Let's try to straighten things out by doing an example here. This will be our last example. Okay, what we're going to do is we're going to design a series RLC circuit that is a band pass filter. And here are the specifications that we have to work with. First of all, we have a capacitor that is 5 nanofarads, and we need to use that in our design. We need a center frequency that is 8 kilohertz. And let's be sure that our filter quality is 2. Okay, now out of this, we need to specify what our R and our L values are. We've already got the C here. We need to know what the low cutoff frequency is, the high cutoff frequency is, and then we can determine the bandwidth from that. All right, well, straightforward. This is what the circuit looks like. L, C, R. Our input is some sinusoidal source with and we're going to be able to vary the frequency so that we can figure out the solution for this. And our output is going to be across the resistor here. Okay, well, omega naught, that's 1 over the square root of LC, which is 1 over square root of L times our C, which is 5 times 10 to the minus 9 farads there. Okay, that's what omega naught is, but this is not omega naught, that's the frequency. So 8,000 hertz times 2 pi, and then let's square that, and that's what is equal to 1 over L times 5 times 10 to the minus 9 farads. Okay, so out of this we should be able to solve for L. If you do that, you should get 79.16 millihenry. Okay, so we've got our L value now. All right, so we've got our L and our C value here. Q is filter quality here, and that is omega naught L over R. Okay, where did that come from? From omega naught over beta, and beta is R over L, so that's where that came from. Okay, then our R is going to be omega naught L over Q, and that's equal to, let's see, 8,000 times 2 pi times 79.16 times 10 to the negative 3. Divide that by 2. Okay, so we should be able to get that pretty straightforwardly. All right, so if you do that calculation right there, you end up with 1.99 k ohms. Okay, at this stage we've got our R, L, and C values here. We should then be able to compute cutoff frequencies. Omega C1, that's going to be minus R over 2L plus the square root R 2L squared plus 1 over LC. And if you do that right there, that's equal to 2 pi f C1. Plug in the numbers, you end up with f C1 of 6.25 kilohertz. So speaking in terms of low frequency cutoff, that's 6.25 kilohertz. We're expressing the final answer in the same form that we were given our original frequency. So that's kind of important there. Okay, you do the same sort of thing for FC2, and you end up with 10.25 kilohertz. I'm leaving this for you to plug in the numbers, do the calculations, and see that. Now, once you've got your upper and lower cutoff frequencies, then you can compute your beta. That's the bandwidth, and that's just frequency cutoff 2 minus frequency cutoff 1. And that's going to be 10.25 minus 6.25, and that's just 4 kHz, so 4 kilohertz there. All right, so we've got everything that we set out to determine here. We've got our L value, we've got our R value, we've got our upper and lower cutoffs frequencies, and then our bandwidth. Okay, so if you were given a problem like this where you were given a certain C value, you know what the frequency, center frequency needs to be, and the quality, well, you could solve this. Okay, in fact, you should probably anticipate a similar type of filter problem, or maybe one of the other types of filter problems on an exam sometime in your future.